we're live and ready to go whenever I'm live.
All right, it's noon. I actually decided to give a seminar at the same time, around the same time I teach. So I just stopped this morning and I had a 45-minute break. So if you don't know me, I'm the newest faculty member here, even though I've been here for a year and 3 months. I am not the youngest, but the newest. And so my name is Mayra Oyola. I think a student yesterday asked me, I don't know how to address you. Is it Merced or Oyola Merced? I normally go by Oyola Merced. Oyola is my dad's last name, and in Puerto Rico it's customary to use your mother's maiden name. It's actually my legal name, but sometimes I drop it. Lately my mom has been complaining about it, so I added that here. Yeah, she's like, you're a doctor and a professor, you're not using my last name? I'm like, yeah, okay, Mom, I'll start using it. So you can call me Mayra. Let's keep it simple, right? I am an assistant professor here. I will talk today a little bit about aerosols, and this is my real original true love. I'm really passionate about aerosol research, and not only to study the evolution of aerosols and understanding the chemical and radiative impacts, but also understanding how they connect with the larger scheme of things. How do we connect aerosols with weather forecasting and things that we actually use on a daily basis, right? So we'll talk a little bit about, actually we'll connect to what happened here last summer. How many of you were here last summer, or this summer, I guess, and you experienced this super extreme, really bad air quality event that lasted for a couple of months, as a matter of fact. So we'll talk a little bit, we'll start home here in the Midwest, and we'll move a little bit more into the African side of things and looking at some of the work that Ruby has been doing, specifically looking at heating rates for a field campaign and how does that connect with radiative transfer. And we'll talk about other research. I don't think I'm going to have time to talk about aviation, but I will definitely talk about ozone and how that ozone nexus connects with aerosol and the regions that we are studying. So this is my background. So if you don't know me, I graduated from the University of Puerto Rico, Mayagüez, went to Howard University in Washington, D.C., came from NASA JPL before coming here. I've been all over the place. First time living in the Midwest. I don't plan on leaving anytime soon. So, and you have a couple of the things that I've been doing for service, heavily involved with AMS. So if you see me around in the conference, say hi too and come help. We're actually looking for volunteers for AMS Women, by the way. And a little bit, again, I talked about my career path. I don't think I mentioned that I was a postdoc at the Naval Research Lab, and that's where most of my data simulation work comes from, my experience. I spent a year at NOAA, at NCEP, the National Centers for Environmental Prediction, and that's where I learned how to run GFS and all that good stuff that led for my dissertation. And at NASA JPL, I was a scientist and also a deputy director for an international office. So I went to the UN several times. It was really great, but I'm really glad that I'm here teaching and working with students. Actually, that's very fulfilling to me. And just so you know, I am teaching 330 and 340. I see some of my students around, so good, bonus points. Okay, so aerosols. I always joke that, how many of you are Star Wars fans? Okay, good, a couple of nerds around here. So I always joke that aerosols are the midichlorians of the atmosphere. Do you know what a midichlorian is? No. Some yes, some no, okay. So midichlorian, technically, in the Star Wars world, are these small, kind of invisible particles that make up the Force. So when you hear in the Star Wars world, people talk about, you know, the dark side of the Force, and then the Jedi, that's what they're talking. It's midichlorians actually making people good or bad, you know, essentially. Right? So I feel like aerosols are kind of like midichlorian, and sometimes when people think about aerosols, especially non-scientists, the first thing that they keep in mind, or they think is, you know, is a spray can. So that's I come from a non-scientist family, and that's the first thing that my parents thought when I talked about aerosols. They were like, why are you doing, like, normally people ask and they talk about tornadoes or hurricanes, especially coming from Puerto Rico, right? A lot of people are doing hurricane and tropical meteorology stuff. So when I told them I'm doing aerosols, they kind of looked at me like, what? It's like, No, Mom, it's not that aerosol. So, but technically, essentially, that's what it is. It's a particle suspended in the atmosphere. But within the context of our planet, those particles have a really big impact. So, as you can see here, this is a GEO's simulation of aerosols. We see several of them. I love this animation because it shows, and I keep using a different one every year, but I believe this is for 2020. So you can see here wildfire smoke, which is the white. We see these dark blue or vibrant blue colors, and here what we see here is actually a hurricane getting entrained into that sea salt or sea salt particles. We can see them here too. As a matter of fact, we see more smoke. My first love in this field, Saharan dust, coming from the African coast, and as you can see, it travels really far into the Caribbean and also the east coast of the US. As a matter of fact, one of the research areas in my group, or one of the events that we're looking at, is an event that happened during 2020, as a matter of fact, that we call Godzilla. And that event actually, dust was found all the way to the west coast. It was very strong. It's like one of these really large, interesting events, because at the source region, it wasn't that special. But the conditions around that actually led for that event to be really impactful over the ocean and also over the East Coast. So, but within the context of aerosol, things that we really want to know. I said small particles suspended in the atmosphere, normally around these ranges. There are many different size, distributions, and sources. So I mentioned sea salt, volcanic aerosols, mineral dust, and it's not just Saharan, there's dust around the world. Biomass burning, so coming from wildfires, fossil fuel burning from cars and other anthropogenic type of activities, and others. So again, here are natural anthropogenic sources. They're important for both climate and weather and climate. That's what I should specify. So climate, actually in climate, aerosols still provide the largest uncertainty if you look at the IPCC. So we still don't know a lot about them. It's kind of like a new science, even though a lot of things have been accomplished in the last 30 to 40 years. But what I really care about is this. They have an impact on satellite retrievals, on the satellite remote sensing person, and they have an impact on numerical weather prediction or modeling. And we're going to talk a little bit about those impacts in a second. I want to take some time to introduce the people in my group, people that have been helping me doing some of the work that I'm going to present today. I don't like using Oyola research group, so we are the Atmospheric Characterization and Observing Systems group. I'm missing a couple of people here. The group has grown. This one is actually still in Puerto Rico, but she has been joining us. She has continued to work in the group with us. But the goal is to kind of find or improve the knowledge of the connections between thermodynamics, aerosols, and convection. So within that, there are 4 areas in the group that we are currently looking at. So 1, aerosol radiative and thermodynamic impact on satellite data simulation and NWP. As I said, my one true love. 2, impact of wildfire smoke, which I said we'll touch in a second in terms of talking about the Midwest. 3, tropospheric ozone, and particularly transport and representation of ozone over ocean, because it's really hard to actually sample ozone over ocean with satellite. And finally, aviation weather, and I'm not going to cover that today. So sorry, Damis, but Damis is my new student. She's there, but I'm going to acknowledge her contribution. Okay, let's start home. So let's talk a little bit about this impact on wildfire smoke. 3 students have helped with some of these, Stephanie, Molly, and Paige. So why do we care? So we know this summer, we had a severe impact from a wildfire. That wildfire was in Canada. And what we've observed over time is that we have this increased wildfire activity that is posing a significant threat to the United States. normally what happens is that most people focus on what's going on at the source region. So whether you are in California, like I was for many years, or in Canada, a lot of the research focuses on the air quality in the place, or something called pyro-CVs, which are vigorous clouds that can actually enhance or create thunderstorms very quickly. But normally one thing that people don't think a lot about is what happens with that advection of aerosol. And not just from the air quality standpoint, which is important because we want to breathe good air quality, or good air, but also aerosols have the ability to modulate precipitation. And what happens with that in the long term? So two theories, or two things have been observed. And it kind of seems straightforward, right? It either enhances convection or it suppresses convection. And that enhancement or suppression is going to be associated with the type of aerosol and the environmental conditions and where that aerosol is positioned in the atmosphere. That's really important. But just so you know, a couple of things that have been observed in the last year is that overall, wildfires had actually helped increase heavy precipitation by 38%, and some of that precipitation is actually associated with an increase in hail by 34%, and large hail, so specifically we're talking about hail larger than 2 inches. And so wildfires contribute to this effect because they actually absorbed heat and they emit aerosols. So that is going to enhance moisture and also limit or help, depending on the case, the aerosol transport, wind shear, and other things that are important for that severe weather formation. Now, what I'm showing here is our time series for something called aerosol optical depth, which is technically a proxy for concentrations of aerosols in the column. And this is for the entire month of June 2023. It's taking out of Mayra 2 reanalysis. And you can see here, starting on the first day of June, we can see several peaks and valleys going on until we reach the last day of the month, where we have the worst portion of that air quality event in terms of actual particulate matter. Sometimes we refer to aerosols as particulate matter. You probably have heard of PM 2.5 or PM 10. We had other peaks related to ozone. I'm not talking about those in here, but just so you know the severity of this event, I'm going to show you what it was last year. And actually, most years, in the last 20 years, June looks like this. So if you look at the values, they're actually less than 0.1. Here, we are getting close to 1 several times. So let's take a look at that event from a better standpoint. So what we see here again is the month of June. The darker colors represents the source of that, in this case is biomass burning, and you can see underimposed, or actually overimposed, the precipitation. So part of the reason what we're doing this is that we're trying to identify areas in which the aerosol is interacting with our areas of heavy precipitation. But again, this was a very quick snapshot of what happened during that month using iMerge, which is satellite estimated precipitation. And then here we have Mayra 2, which is reanalysis. So the aerosol portion of the reanalysis for Mayra 2. Now, again, why, then again, what? A couple of things that we noticed. So, close to that peak, the original forecast, or the original 3-day forecast from GFS, had us in a forecast of around mid-50s or mid-80s. The actual temperature was 80 degrees. The chance of precipitation was 40 to 60%. We had nothing. So obviously, things change, and they change very quickly. And why is the forecast so bad? Well, obviously, there's something that is not accounted for necessarily in the forecast, which is the aerosol effect. So what happened? Is it suppression by cloud physics, radiation, we're actually studying about it, but in our, now in our little adventure, what we're gonna focus on right now is on the radiation. Now, how many of you remember heating rates from class? Let me see. I'm looking at the back. So what is a heating rate? So if you don't remember, this is from Patty's book, simplified, actually this is a simplified version of a heating rate. But what a heating rate is, it has 4 terms, is the rate at which temperature of the air is going to change with respect to time or altitude. So here you can see that there's some implication about that atmospheric composition via density, so how density changes with height, and we see our constant, our CP, and we see all these 4 terms, some of them representing radiation that's coming from the surface to the top, which is this arrow over here. Some of them representing radiation that's coming from the top down, arrow down, and 2 other terms that look very complicated with weighting functions, and they are complicated, but these 2 terms actually talk about the different layers in the atmosphere, right? So in a nutshell, these heating rates are going to change or are going to be impacted by solar radiation or long-wave radiation, absorption and emission, so this process is in a long wave, and also heat transfer. Now, so what? Why do I care? This equation. Well, let's look at what happens in a model. Here we have, when you calculate those heating rates, some in the short wave, others in the long wave. Each different line represents a different approximation to those heating rates, right? So they're telling me distinct information about how that temperature is being weighted in the atmosphere in the short wave, and likewise in the long wave. What happens with the actual parameters in the atmosphere when they are different? Well, guess what? Look at the differences now related to temperature, geopotential height, and moisture. And I'm pretty sure John will say that this is going to be a very different forecast if you use some of these profiles versus the other. So that's what we wanted to know within the context of what happened here in Wisconsin. Now, we need, in order to be able to calculate or account for proper heating rates in the atmosphere in the presence of aerosol, we need aerosol information in the vertical. So again, I explain or show these AODs, aerosol optical depth, which are technically, yes?
Just to clarify, so these are the temperature differences due to the aerosols in some kind
In
of model?
well, in this particular way, yeah, GFS. So in this particular is different heating rates. So different heating rates, when you run your forecast, will lead to different or different final conditions. So that's not necessarily aerosol, it's overall. So it will include your moisture, your temperature, your aerosol, etc. Well, I'll narrow it down to the aerosol effect. Thank you for your question. So one thing, if you noticed, there's a dependency, even in the equation, with height. I talked about AODs. AODs is a columnar average of concentrations. However, in order for us to be able to account properly for the aerosol effect, particularly when we do our radiation calculations, height is extremely important. Where is that aerosol located in the column? And that's why we decided to take advantage of an instrument that we have in the roof, which is called the HSRL. And that night I was bored and I started plotting stuff, and then it occurred to me that with the extinction and the backscatter information, so how much energy the aerosol's attenuating and how much energy is scattering, you can actually get information about that columnar behavior or pattern for the aerosol, and then you can bring up something called the radiative transfer model that can eventually give you out those heating rates. So that, this particular model is called fully algo. Now I'm going to show you an example of how does that look like in terms of what we observed. So I'm gonna give credit to Paige, who actually, we've been doing calculations and she helped me with some of these. So this is for the 28th, which is the second highest day of AOD or aerosol concentration over us during June. And these are the times going from 00 to 23 UTC. Now, actually local time. What you see here are the heating rates, again, for the differences of running a heating rate without aerosol and aerosol. So these lines are actually deltas. So you can see that at some point in the day, it doesn't really matter, mostly because you don't have any solar radiation coming on. But then later in the day, the difference between the actual known aerosol and the aerosol profile, it starts about 8, and this is Kelvin per day, units are missing. So what we see here is that we can have some sort of an explanation of what's happening in terms of the impact of that aerosol during that particular day. Now, recall, if you see it here, it's not just one line. It's that these aerosol, or the assumptions that we make about these aerosols, are that they are small, so they're in very similar wavelengths as the shortwave, so they are what we call active in the shortwave. So we see this particular distribution. That's not the same for infrared, for smoke that can change for other aerosols. The larger the aerosol, for example, dust, they tend to be more active on the infrared. But here what happens is that all those lines are technically together. There's still a difference, but it's all the lines are technically on top of each other. Now, that's on us. And again, this is just research that we started. The idea is to put this in a model and actually run several cases to see what happens. But let's move further into the Atlantic Ocean. And I have Ruby and Paige who have been working. Ruby has been working a lot with Fuliagu. I think at some point she wanted to kill me. But it's not an easy model to run. If someone has run it here, they know that Fuliagu is very hard spectrum based, and it's a little bit of a pain. But again, let's go back into the basics of the aerosol. Normally, when you have aerosol, you have incoming solar radiation, outgoing solar radiation. It's a very basic way to look at it. In the case of a smaller aerosol, the small aerosol tends to reflect back that solar energy or that energy into space. A large aerosol tends to absorb some of that energy. And within that context, that's why we have scattering aerosols, ergo what we just showed, what I just showed, and absorbing aerosols like, or coarser aerosols like we will see in an example. Now, what's the problem with models? Aerosols are not really well represented in numerical weather prediction models. They have been, we have gone a long way since I started grad school, which is fantastic, but still we have a lot of issues, mostly because we do not have instruments that can continuously sample profiles of aerosols in the atmosphere. And the one instrument that we had, Calliope, is dead. So there are some instruments that can help, but ultimately we need a better instrumentation suite in space to do that. Even with that, there are some limitations on how you can do those retrievals. So therefore, when you do your data simulation in the model, you're going to have a poor representation of that in terms of the 4D distribution. Now, the other thing is that we really do not understand the physical and chemical effect quite yet. They're not well constrained. So we have, and they're very hard or computationally exhaustive, meaning that we have averages or very basic understanding. That's what we call in those parametrizations, the best that we can do, honestly. And the other thing is that aerosols in NWP, you have to have the change every 3, 6, 9 hours or whatever it is that whenever you run your code, right? In a climate model, you normally have an average over a long period of time. So it's easy, for example, to pinpoint things like Saharan dust because you already know where that air mass is going to versus something like smoke aerosols that are very event dependent. Now, when I first started grad school, and this still is my motivation, I saw this plot and I fell in love. And it looks terrible now, because, I mean, the quality has, I mean, we have a lot of stuff. I started grad school 10 years ago, I think, yeah, 12 years ago, so it's not that long ago, but still. What we see here is satellite observations of what we call outgoing long-wave radiation. We have a model with outgoing long-wave radiation, and then we have the difference between the model and the satellite. And that's for July 2003. The satellite's Mediasat, and the study was done using the Met Office Unified model. When you actually calculated the differences, you see a bias, a large bias. And this large bias falls over here, over West Africa. And particularly in this region. If you can see the actual values, they exceed 35 watts per meter square. So what they found with this study, which was very amazing to me, was that this difference made a significant impact on how much precipitation was falling far away from the African coast. Where the precipitation was, the band was actually moving, and also the temperature. And that, for me, that was my start to get like really intrigued about data simulation, and then specifically that aerosol effect.
And that difference, that bias is due to aerosols?
Yes, so that is there, the Saharan dust. So technically the source region for the Saharan dust.
Okay, so that's not
Yep.
convection?
No.
Like usually we use OLR
No.
to...
No, so that's actually, I believe that at this point some of the precipitation was actually removed from the run. Okay, so data simulation, what is it? So most people think about data simulation at, oh yeah, I'm just going to bring a lot of information into the model. So normally when you run a numerical weather prediction model, you have two boxes. You have a data simulation box, and then you have the actual model physics and dynamics box, which is what we call the model. Model dynamics, all the equations are there, and that's where you get your outputs. But as important as the model is, the data simulation also brings a lot into the accuracy and the actual performance of the model. So data simulation, what it does is finds the best estimate, or it uses the analysis of the state system, given a previous estimate of the state or the background. So what does that mean? I'll simplify it for you. Normally when you run a model, you have an estimate, and that estimate is your information from the previous model, the output from that previous model. And what you get now is that all the data that's coming in. And that difference, and this is a very simplified way, trust me, this is a lot more complex, but that difference here, it's called the innovation. In the data simulation world, if the innovation is really large, the data gets discarded. Normally they try to correct it, but honestly, if you don't have time, you only have 3 hours to run all the models, get all the observations, do all these things, you have to simplify the process, so a lot of that data gets rejected. So what we found out is like, okay, so what's the impact of that rejection? And this comes out of my actual PhD dissertation. What we were doing here was identifying which areas were more prone to get rejected. And again, this is the African continent. This is a simulation, satellite brightness temperature simulation for AVHRR. I believe we were using channels 4 and 5. And what we see here is that in this difference between observations with dust and the simulation with no dust, we found these areas in which there are innovations larger than 10 Kelvin. So back in the day, I've been trying to get, but back in the day it was really easy to go online and see how much data NOAA and NRL and all these centers were throwing away from satellites. And it was a lot. So that kind of led me, after my dissertation, to go to NRL, as a matter of fact, and we were focusing, so AVHRR is an infrared sensor, but then I switched into hyperspectral infrared. And I know, Larissa, you had some questions. I was online last week about hyperspectral infrared. I'll mention something about why you shouldn't be using those profiles for what you specifically do. So, why the importance of hyperspectral infrared we see here is that normally for vertical profiles, which are again very extremely important for heating rates and other processes in the atmosphere, we get coverage in the developed areas of the world and very little coverage where we don't have any a lot of development or developing countries, and also over the ocean. So the hyperspectral infrared is extremely important because it does provide us that extra coverage with temperature, pressure, and moisture profiles. So instead of having, for example, 152 soundings or a little more in the US over a day, now you can have a lot more, and overall it's over 300,000 per day using, this is Chris, by the way, Chris, which is one of the hyperspectral sounders. Now, when you go into the data simulation system, and I believe Bill talked about this last week, there is something that we use, which is called the FSOI, the Forecast Sensitivity to Observation Impact. And a very simple way to put that is that here are your satellites that get assimilated, and this is the impact that each satellite has in reducing the 24-hour observation error. Now, if you look at the top, you see that the highest bar, so the instruments that have the most impact at NRL are the ones that have to do with infrared sensing. Now, these, depending on the sensor, might change from microwave to infrared, but again, they have a significant impact. Now, what happens is, when you use that spectra from one of those satellites, and here we have, again, simulated Chris for 1300 or 1305 channels, and you do not account for dust, you see a significant differences when you do that calculation of brightness temperature, particularly in the atmospheric window, which is what we use to obtain most of our retrievals. So you want to make sure that you account for that dust effect. Now, the problem is that infrared sensors are or dust is active in the infrared. So for those aerosols, that kind of difference is going to be a little bit larger. And again, this is the average, I should have said, the average in the tropics using 200 profiles over dust. It's collocated with dust. Now, what we did at that time was, well, all of that data gets rejected. Is there any way that we can actually tell the model that this innovation is not a mistake and fix it? So the one thing that we need to do is kind of identify which satellite pixels are actually dust or dusty pixels. So what we did is that we used a model that the Navy has, which is called NAVGEM, and also NAPS. And with NAPS, we had an idea of what the aerosol profile was and the conditions, particularly in our region of interest, because again, remember, NRL, Navy, they care about the ocean, so we were looking at that particular region. And we created a configuration that used a radiative transfer model that's called CRTM, Community Radiative Transfer Model, in which we actually add that identifying code, ran our RTM calculations now specifically for that aerosol profile, had our new brightness simulations, but now within the solver, which is what rejects, we were telling the solver to not get rid of this data, we need it. What does that look like in the end? Well, this is actually one of the many cases. We ran this for months, but this is a particular case here. You can see where we have the aerosol from NAPS. And that's actually a really large region over here, but we were again focused on the Atlantic. Normally, these red areas would have gotten discarded or rejected, and now they were included in the model. We ended up increasing the number of observations post-quality control by 20%, and that had an impact in the model. And this is the no aerosol. You still see gaps, right, in here. Those gaps are not associated with dust, they are gaps associated with clouds, which is another problem. When we do the cloud, the community actually started moving to this all sky data simulation, and now we're trying to do machine learning to try to solve that problem of how do you not get rid of that cloudiness. Now, again, why do we care? How does that improve the forecast? Here we go. Eventually, that goes back into our heating rates and back into what we had before, just as a reminder. But more specifically, and moving forward, what are we doing now is actually utilizing and maximizing observations to look at how we can link this back into the data simulation world. And we are taking advantage of CPEX, which you probably have heard from Angela and others in here that have actively participated. This is actually Ruby's, I don't want to steal her thunder because eventually she'll be presenting, but what we see here actually is one of the days, a very interesting day in CPEX AW, or CV actually was, where we have an African easterly wave. I think that's the one that led to her mean on the 22nd. And the blue line is the flight path, so it was heavily sampled. The brownish area is the aerosol, and then the actual, obviously the colors, the radar-like colors are emerged precipitation. So we had that for us to understand where things were sampled relative to the wave, and also where the aerosol was relative to the wave. Now, Ruby did this for many days, and during the field campaign. And what we see here is, remember that I said aerosol distribution is extremely important. Now, what we see here is a combination of multiple profiles obtained from CPEX, from the extinction, in aerosol extinction, in which they were using a LiDAR, so this is the actual truth. And then we see here the standard deviation or the variability of those profiles. And we calculated extinction for Mayra 2 reanalysis, in which some of this data got assimilated. And likewise for CAMS, which is the European aerosol reanalysis. And we can see that these two lines look very different than the actual observation. I am not surprised. I've done studies like this before. We found several things like that. But it's now we're pointing towards issues with the actual aerosol model and the aerosol representation within reanalysis. Now, likewise, as we did with the other case, here is a calculation of the heating rates. And what Ruby did, she divided this into two, she characterized them as high dust cases and low dust cases. So for high dust cases, we had aligned a heating rate calculation for Mayra with aerosol, and then Mayra just the standard pressure, temperature, and relative humidity profiles going into the radiative model with no aerosol. Same thing with CAMS, and then same thing with the CPEX data, which comes from an airplane and the LiDAR. And what you see here, again, you have the short wave, the infrared, and then the total heating. I mentioned it already, that the actual Mayra reanalysis assimilated some of this information. And what we see here is that these are the no aerosol runs. The blue line, again, is the CPEX one, which we consider the truth because it's the actual observation. And then we see the Mayra, which looks kind of similar, but then the big difference, obviously, in CAMS, which normally tends to be esteem a better model or better reanalysis. Obviously, it didn't have a simulation, and we see this high overestimation of the heating rates at the lower levels of the atmosphere. Now, I want to make sure that you understand or pay attention to at which levels this particular difference is. So 900, and then we see something at 800 and 700. So if you're a forecaster, you will immediately look at those levels and think about what are the processes that are important around those levels and why that difference will impact your forecast, right? Similarly, we have infrared heating. Here we see a little bit of a difference more on the CPEX. Most of the reanalysis looks the same. And here, finally, in the total Again, very reflective of that short wave because it was more like in the morning time, I believe. So we see that those difference between the profiles. She did the same for, again, this is high dust. This is an event where we had low dust. Still see that tendency of CAMs to overestimate. And finally, what I just want to put here is the actual difference. So this is how the heating rate looks compared to the CPEX heating rate. And again, when you don't have to worry about the aerosol, both reanalyses kind of look very similar. There's some differences at the bottom and at some point in the upper atmosphere, but when you particularly look at the aerosol, you can see that massive difference between the reanalysis. Yes?
Is it possible to quantify how that translates to like a delta function at the surface heating in the model? Is there an output that
Yes, so you can use this to do that. We haven't done it, but yes, you can use this to kind of look at that particular problem as well.
Is it kind of about 2 Kelvin per day difference for the surface, or is it more? Negative, it'd be the opposite, right?
In this particular, well, just for this, I think it's 2 Kelvin, yeah.
Like I'm imagining if there's more aerosol, the surface wouldn't be as hot, and so you get less convection.
Yeah.
It's absorbed in the troposphere.
Yeah, true that. So one of the things that we're going with this is actually my idea is to get a model like MPAS and interpolate the aerosol to the mesh, MPAS mesh, because you have that high resolution to look at things like that. So far we don't know. We're estimating from just the radiation.
If you're gonna look at the surface impacts, you would need an interactive surface too. You would need
Yeah.
A mixed layer model ocean.
Yeah, and so those are like multiple pieces of work. So yeah, I think tackling one part at a time. Yeah, we get to look at the surface and then potentially just look at the aerosol and then start looking at how it's influencing all the different layers, or moving the aerosol up and down also too in those simulations, which is something that I've done before in the past. So yeah, this is again research that we are currently under development, but I think there's the potential for a lot of applications. And the next thing that we're looking at is actually, now that we looked at this, and we know the potential limitations with Mayra and CAM, but we also have the initial data set for these waves as they were developing off the coast of Africa. So part of what we want to do is actually run the radiation as the wave moved out and see the differences in the radiation in different areas of the African easterly wave, like looking at different quadrants, etc. Now, I have, I think, about 15 minutes left. So I'm going to switch a little bit and talk about ozone. And while ozone is not an aerosol, it's involved in aerosol processes, and it's involved in this same region of the west coast of Africa, which is extremely complex and very exciting. And actually, these observations that we're using here were obtained on a field campaign years ago when I was a grad student over a ship. So most of the work has been conducted by New Deb Rivera Maldonado, who's at the University of Puerto Rico, and she kindly has been connecting every week to try to work with this from a distance. So I needed to give her the credit. So why study ozone? We know that tropospheric ozone is hazardous, it's important, and that ozone budget is controlled by photochemistry and transport, but also weather. Weather is something that we do not live in a laboratory, we live in the real world, so that's something that we need to account for. So we've seen an increase in tropospheric ozone since 1850, which can affect radiation physics and weather formation, not only in the real world, but also in the models. And the problem with ozone is that satellites and models tend to really do a bad job with ozone in the stratosphere. Those are limitations with the satellite sampling. So more often than not, this is actually very limited to in situ data and just to coarse estimates. So just as a reminder, there's something called good ozone and bad ozone. Good ozone is the ozone layer higher up that protects us from evil UV rays, and where bad ozone is near us because that can actually act as a pollutant. Okay, get that in class. So why do we care about ozone within this region? So particularly speaking, as I said, we are looking at the interactions with weather. And ozone can be either transported or formed by various processes. So near the surface, you can have things like biogenic, volatile organic compounds, and wildfire emissions that are precursors for ozone formation. In the middle of the atmosphere, you can have lining. Lining releases NOx, or nitrous oxides, and that's a precursor for ozone formation, if you didn't know that. We can have stratospheric, tropospheric ozone exchange, where you have a folding event or a major weather event, and you get some of that higher or rich stratospheric ozone pushed down, and also by actual weather shifts, so monsoon cyclones, heat wave fronts, and things like that. Now, biomass near the surface, it's something that's also of concern as a precursor, and we can see here some of the more prevalent biomass burning regions in the world. And again, going back to Africa, we can see that this is one of the hot spots, and right there where we were also looking at Ruby's research. So one of the things that we want to know, since this area is so complex, is what happens. We know what happens sometimes at the source region, but what happens downwind of all of these sources, particularly here in the west coast of Africa. So 2 assigned questions based on that. 1, how effectively atmospheric models can capture ozone and ozone representation in the atmosphere, particularly over the ocean, considering the utilization of satellite data in assimilation processes. So again, we link back into the satellite data assimilation process. And how can we enhance our comprehension of factors that influence vertical ozone distribution, including things like stratospheric intrusion, regional weather patterns, and biomass burning. So in order to do that, as I mentioned before, it's better to go out. So we are using profiles, actual ozone zone profiles from the Aerosol and Ocean Science Expedition, which is a series of field campaigns that have been going on for quite a while, I believe 2006. It's more than 12 field campaigns at this point right now, but the purpose of AEROS is to study physics, meteorology, chemistry, and do satellite CalVal. Some of that data is actually used here at SIMS. So there are about 250 ozone zones and counting that were used, that can be used for research like this. And just so you have an idea what an ozone zone looks like, this is the actual package. It's a the ozone sensor, the ECC ozone sensor has a cathode and an anode. You can put a potassium iodide solution between 2 chambers. Technically, very quick explanation. There's different concentrations. When the air gets into the tube, it gets pumped, it gets into this. Depending on the ozone concentration, there's going to be a reaction between the cathode and the anode, and you're going to get a voltage. That voltage can be translated into ozone. So this is how it looks like when it's put together. That's my advisor, that's me, who was actually training me at that time on how to launch them. So you can see they're really huge, but very fun to launch and very difficult to prepare before. So if you've never seen a launch before, that's how it looks like. So everybody's wearing gloves, yellow gloves, holding the balloon because they can rip. Your oils can actually rip the balloon. So that's the team holding the, it's very windy, and obviously we're in the ocean, you can see the choppiness. And so you'll see the launch. That's the payload. That's me. And at some point, someone's about to fall off. You don't want to fall in the ship, it's hard, and yeah, you can get injured easily. So. But yeah, these things are very hard to do when you are overseas, and you have to have a really good crew manning the ship that collaborates with you. Some people can't do it. You can see all the obstacles that you have around. So for this research, we are showing here November 2013. Lucky November 2013, that was a special cruise for me, that's why I chose it. Also, it was very interesting. But what we see here are the locations where we actually launch ozone zones. And particularly, we focus on this region over here, which is a very special transect. We call it 23 West transect. Beautiful because you can get all the advection from dust, biomass burning, and other things associated with the jet. And again, if you don't remember the region, that's why we had that. So the idea was to look at the ozone profiles that we had and identify various mechanisms within that profile. And if you remember from your dynamics, there are Rossby waves and gravity waves. Rossby waves can create ozone filaments because you have that transport. And normally, ozone is associated with quasi-horizontally or quasi-horizontally transported ozone, and then gravity waves, which tend to be more associated with that vertical displacement. So that's how that ozone profile looks when we change it to PPV. We cut it off so you don't see the inversion here at the top, because we're mostly focused on the 20, or basically on the tropopause and below. But what you can see here is all of these little variations in ozone. And that's what we call the laminar. And with that is that we apply the laminar analysis. And the laminar analysis, which Brad, who was around here, was actually something that Brad worked on for a long time, allows us to identify if it's a gravity wave laminate or a Rossby wave laminate, depending on correlations with potential temperature. So, technically, if you have a poor correlation, you get a Rossby wave. If you have a strong correlation, it's a gravity wave generated ozone. And as you can see here, this is an example, but a lot of our data looks like that. These are the strong correlations. The pink are the weak correlations, so Rossby wave ozone, gravity wave ozone, and a lot of the column is gravity wave generated ozone, which is very opposite to what most literature says, and including my own. And the reason why is because most of that sampling was done in the mid-latitudes. So obviously, let's look at what was happening in the tropics then. This is the location where that profile came from. So you can see a lot of convection. Here we see the dust, here we see the biomass burning, the black line here actually denotes, it's a back trajectory analysis, so it's where the air mass is coming from, and it was run to 240 hours, so 10 days. So here, it's only shown, I think, at 5 days at this point, because it got cut off. But this is the location on the ship. So these are the weather conditions surrounding that sampling. Now, as I said before, we repeated this for a number of campaigns, and what we found is that most of the budget is gravity wave generated, which is against what literature says, but again, different sampling region. A little bit is Rossby wave generation, and some is what we call background, which is its age, and we cannot really determine its origins. Now, finally, the takeaway from this ozone part, and I'll stop here, is why do we do this? And I said at the beginning, models and satellite models are bad at representing ozone because mostly satellites are bad at actually capturing ozone. So this is reanalysis, and again, I go back to Mayra 2. This is ozone, and you can see particularly this from the soundings for that same field campaign that I just showed in 2013. You can see, you don't have to be an atmospheric scientist to just pinpoint the differences between the two. So it's a lot of work to be done. And part of what we want to do is actually incorporate some of these profiles within Musica and then take it from there and see if there's some improvements to the ozone and what that ozone is actually doing to the systems that are nearby. So again, summary, and I guess I'll have 5 minutes for questions. These are my contacts. If you need questions, you know where to find me, 1343 upstairs, and I'll just open the floor for questions. Yeah, that's a good question. So it depends on the model, but normally what happens is that most models have like sources and sinks. And so the sources get activated if you hit a wind threshold. For example, for aerosol, I believe it's like 10 meters per second. So once the weather conditions exceed certain range, that advection gets kicked on. But the assimilation kind of is there in the window. So it's independent of the actual source and sink path in a way. It's kind of indirectly independent, but that's how it works, yeah, in a nutshell.
And then it's transported.
And then it's transported, so every number of hours, depending on the assimilating system, you get a new round of observations. And depending on that new round of observations, you get that adjustment to the forecast. Hold on, first there, and then.
Yeah, so as a follow-up to that, when you make the correction or when you like include the observations that were initially getting rejected, are you making those corrections just to like the temperature and the pressure, or are you also making them to the amount of aerosol that's there? Like, does the model know?
So you have to tell the model, and that actually is a problem sometimes, because if the model is not ready or prepared or doesn't have the code to accept the new information that you're inputting in the model, then you have an issue. Or sometimes, especially models that get tuned in certain ways, so when you change the aerosol, even though you are opening that rejection field, you're opening another can of worms sometimes somewhere, and that's I mean, it's kind of like a black box, so sometimes that's a problem. Yeah, that's a good question. It depends on the model.
And then you focus mostly on African dust.
Yeah.
Is there differences between how you would include that sort of aerosol into a model versus like the wildfire smoke recently that we've
Oh yeah,
seen?
yeah, absolutely.
Okay.
Yes. Yeah. Again, sources and sinks are easy for dust, right? Because you know where the major areas, and there has been substantial research over time. When you're talking about biomass burning, then that's a new problem, because sometimes you don't know, right? You get a fire, it starts.
It seems like for forecasting purposes, it would almost be easier to not even try to model where the source is coming from, but just to see where the source is coming from, and then tell the model, like, there's a wildfire here. Like, we can tell now, but you shouldn't be trying to.
So there's a lot of, that's a good point. So there's a lot of research that's going into now trying to look at if you can predict if an area is prone to fire. So you can do things like that, like tell you, okay, this area might be prone to fire, what happens in the fire happens. Yeah, but it's that's where the research, that's where the money goes now. John?
Yeah, Mayra, very interesting. I don't think I understood about the production of ozone by gravity waves or Rossby waves.
Yeah, I went very quickly through that.
Yeah,
So,
is it that you're moving other chemical species into a different environment that allows a chemical pathway to production of ozone?
yes.
Oh, okay. That's what's going on.
So in the mechanisms of ozone, the photochemistry is important, but the transport is too. So the transport of precursors is an important one.
Okay.
It could be a transport of precursors where you're moving something from point A to point B and then it's chemically formed there, or you're actually moving ozone from another region where ozone was into a region where ozone wasn't.
But that's called transport, not
Yeah,
production.
so that would be more transport.
Okay,
yeah.
so
Transport and production, yeah.
So off the coast of West Africa, you have thunderstorms with presumably some lightning, and you have this stuff from the wildfires
Yes.
that kind of get their act together.
And
to produce
stratospheric
ozone.
intrusion
Okay,
too from
yeah.
the
On the northern end of that.
Yeah, yeah.
Okay, that's very
So it's
interesting.
very complicated. It's very complex because of that.
Yeah.
Online question from Dave Henderson. When modeling aerosols and heating rates, the aerosol optical properties, single scattering, albedo, and asymmetry parameter, can make a large difference in
Yes.
shortwave and long-wave radiative transfer. How do you represent the aerosol particles, and how sensitive are the results to your assumptions?
That's an excellent question, and I skipped that because most of the people normally don't ask that unless you're doing aerosol, but that's an excellent question. And so for most of the things that we're doing with Ruby, we're using Gokar climatology. So within Mayra, there's actually a distribution of aerosols that has aerosol size and density and assumes it has a lookup table for the optical properties. So we choose those, and even in the extinction calculations, we have to use some of those well-established OBA climatology characteristics for the aerosol. And that's not just very specific for Mayra. That's very specific for most of the aerosol models, or CAMS, Mayra 2, even the numerical weather prediction models tend to use this OBA climatology for the optical properties and other characterizations for the dust and other species. So it's not just dust. They have these 16 or 17 different species. Yes.
For the downwind North American fire effect, I could imagine some long-wave pattern where something producing fires would also simultaneously make more thunderstorms downstream because of the dynamics alone. Do you have the capability to turn on or off aerosols and evaluate that?
Yeah, so that's things like the new model H4 and that they have that online radiation, and same thing for research. Technically, that's what we want to do. It's to be able to turn on and off the aerosol, because also it's not just the physics part, but also the computational side. You don't want to have extra calculation if that amount of aerosol is not doing anything, right? So yeah, that's something that you can do within a model. Again, the models that have like the higher resolution, other than Musica, for example, if you think about MPAS still doesn't have any aerosol, so you kind of have to go around it by doing that mesh interpolation and then working with it, which is pre-proposed. Let's see if we get funded.
Sounds like
It's a different thing. Yes.
Super interesting talk. So your title, and I walked in a little bit late, so maybe you already said this, but I guess your talk and kind of your research path is based on the idea that better representing aerosols in numerical weather forecasting models can improve forecasts. Am I understanding that correctly? Yeah. So
That-
to what existing evidence is there for that, / what is the kind of smoking gun that you want to provide that that's the case?
From previous research,
From previous research, to what extent does that already exist?
So that exists. So actually, part of my dissertation was that. I actually had to put aerosols in DFS, in a version of DFS, to improve SSC retrievals. And you see that improvement. And there's a lot of other research that has been done out there that does that. That they actually shows that impact. We still have a long way to go. Because it's more often than not, and actually most of the models actually also now have aerosol too. But more often than not, you have these limitations with either knowledge of the aerosol and also characterization and computational resources. It's not, and it's a very expensive process to run.
So your goal is to provide further evidence that this.
Further evidence
big picture goal
and
that
also
this-
having technology transition. So ultimately, my dream would be to have technology transition to a major office and then prove that we need satellites that can get this vertical distribution of aerosols. And if we can get an EBI that can do that with nanosatellites, cherry on top from my yeah. I think we passed a lot of time. Well, thank you.